So, guys, don't get the misunderstanding, the misimpression, the wrong impression. Class is never going to go like this ever again, but today it's going to, because frankly it's the best way to handle this. So do this. If you're not with me yet, we're on page 77 there on chapter 3, which is all about stoichiometry. Remember when you learned that word? And guys, if you remember in general chemistry, we covered stoichiometry over the course of about 3.5 to 4 weeks, starting sometime in January, late January, moving into February, and we spent a big old long time doing it. We're going to do it today in a day, which is actually more like the pace you'd tackle something like this at a college level. Here's what we're going to do. And again, we'll never do this again. This will be the only time in class that we will actually allow the book to drive the order that we learn stuff. We'll go sequentially through the chapters as it leads to units, but today literally it's just going to be page 1, well, page 78. What do we need to talk about? And we're just going to march through chapter 3 today. So guys, don't do this with me, but do this now. Just allow yourself to sort of page through chapter 3, maybe read the headings 3.1 and so on, and just get a general sense of what chapter 3 is all about as it relates to stoichiometry. Then we're going to march through this page after page after page. And guys, this is going to be very bi-directional. If you want to stop and spend some time about reaction types, if you want to stop and talk about that, hi Vanessa, sorry I didn't know that was locked. If you want to stop and chat, that's fine. If we as a group feel like either A, we remember it, or B, we could catch up on it on our own, then it's probably not a good use of time and we won't dwell there. There are, though, guys, some things that are not going to be optional. There are going to be things that I know are new that we do, in fact, need to talk about, and I will draw our attention to those as we go, and we'll go through chapter 3 today. So go ahead and spend a second and page through the chapter just to give yourself a sense of what's there, and as soon as I pull up the notes on my phone so I remember exactly what we need to look at, we'll be ready to go. All right. You guys ready to tackle this? I'll give you another second. A lot of it sounds familiar, right? Yeah. By the way, guys, your summer quizzes have been scaled to 50 points, and I have them on paper. I don't yet have them in Skyward, and frankly, because today's a short day, I'm not going to hand them back to you because we won't have time. I'll give them back to you on Tuesday. And then what I'm going to ask is that we wait a week or so before people start trying to retake the quiz if you need to. Frankly, just because the beginning of the year is so busy for me that it's frankly something that I would like to postpone just to give me a little more space to do other things. Okay, you guys ready to go? You okay? Are you good summary? Okay, so guys, go back to what I think was 78. Was that the first page of the chapter? Yeah. So go back to page 78, and we're just going to start chunking through this. I will mention maybe some things that I think are big ideas. If you want to contribute, great. If you want to ask questions, super. If you want to go, hey, we're good, let's go, then we'll go. So guys, the first thing that we run into in this is this idea of balancing chemical equations. I think most of you felt a high level of success with this. Remember though, guys, why do we balance chemical equations? What is it that we're actually doing? What's the larger principle that we're drawing on when we balance chemical equations? Which is called what? Good for you. We can't create or destroy matter. Law of conservation of mass. So guys, when we balance equations, what we're doing is we're bringing those equations into alignment with the law of conservation of mass, good on you, that says that we do not create or destroy matter during chemical processes. So to do that, it becomes that crazy tennis match of put a number here, put it there, back here, go here, do that, do that. And when the equation is balanced, two things will be true. One is that you'll have the same number of atoms on both sides. But guys, the other thing that you've got to keep track of, because they're real sticklers on this in AP, it will always be in lowest terms. Do you know what I'm saying? So let me show you an example. So for example, if we balance an equation like this, and we've got 2H... Awesome. Hold on. I've got to quit out of this. I've got to restart it. And now I've got to go over here and open this back up and now go here and, okay, here we go. So guys, if we have something like this that says 2H2 plus O2 yields 2H2O, balanced? Yeah? What kind of reaction is this? This is the book calls it combination. Remember when we talked about the idea that different terms in different books, different places mean the same thing? In AP, we've got to move past that because we will run into different terminology. The book calls this a combination reaction. What did you learn it as last year? Synthesis. Is it endo or exothermic? Do you remember? All synthesis reactions, with a couple exceptions, are exothermic reactions. But guys, here's the thing. You could also balance this equation like this. This works. That balances, but it's not right. Guys, when you balance equations in this class, it's always understood, whether it's mentioned or not, that they've got to be balanced in simplest terms. Okay, so do we need to talk more about balancing chemical equations? Go ahead. What's that? Did I do something wrong? Oh, there should be a 2 here, huh? Sorry. Yeah. Are we okay? Okay. Are we okay on balancing equations? Do you guys remember the tricks that we gave you last year that make these things easier? Do you remember those? We talked about the idea of balancing oxygens last. We talked about the idea of balancing polyatomics intact if you can. Do you remember that? If you've got a nitrate here and if you've got a nitrate there, don't try to balance the nitrogens and the oxygens, balance the nitrates. And then we talked about the idea, do you remember the odd-even conflict that we run into frequently? Where you've got, you've got an odd number of atoms on one side and an even number of those same atoms on the other side. And what did we do to resolve that? Double the odd number and then start over, because you take an odd number, double it, and it becomes even, and then it will balance. Are those things coming back to you? Okay, so guys, is there anything else there that you want to talk about relative to balancing the equations, with the understanding that you'll be working on these in homework just to give you some practice to make sure you know what you're doing? You guys all okay with the fundamentals? Okay, good. All right. So guys, after balancing equations then, the book goes on and it starts to talk about what they call patterns of reactivity, which actually for us is just reaction types. And so as we get into this, and notice we're just going through chapter 3, guys, it brings in these 3 reaction types. I think it was, Caleb, was that you that said combination? Somebody, oh, okay, yeah, so guys, if you look on, there it is, on page 82, it talks about combination and decomposition reactions. Remember, we learned that as synthesis and decomposition. Those words are equivalent, combination and synthesis. And then it also mentions combustion. Guys, what are the 2 reaction types that you learned last year that are not mentioned on pages 82 and 83? Single and double displacement, and they're actually pushed further back into the chapter. But guys, those are the fundamental reaction types that you need to know right now. Synthesis or combination, decomposition, combustion, and then single and double displacement. So those at least if they're superficially familiar, you should have enough to draw on to reconnect to those as you get into the homework tonight. So do you want to talk about any of the reaction type stuff? Yeah.
I have a question. It's kind of irrelevant, but it's not.
That's fine.
So when it comes to AP testing,
yeah.
does it matter if it says it?
Absolutely not, no. And that's one of the things, so when they grade the AP test, here's what they do. They actually come up with what they call the working solutions. And so the person that wrote the question is the first person that gets to propose the answers. Then what they do is they take that answer key and they push it out to the people that are called table leaders. These are people that have been grading AP tests for years, and they get to sort of be the first people to put eyes on the key. Then what they do is they grab a random sampling of the students' tests, and the table leaders grade them against the key. And one of the things they may see is, oh, we wrote this, we said the answer was a combination reaction, but some people in Utah call them synthesis. And then they'll go backwards and they'll go, oh yeah, that's valid, let's add that to the key. And after they error check the key to allow for those differences that are both correct, then they come up with a universal key, and that's when they start grading tests. So, no, you'll be fine. So, and we'll talk about that, guys. We'll talk about, here's a term throughout the year, here's another way you may hear about this. And so I'm pretty good at covering those bases. So, yeah. All right, you guys good here? Are we good? All right. So where does that take us then? As we continue on, we've gone through combustion. Now, guys, we're ready to talk about atomic weights. Are you trying, are guys, in your head, are you putting together the way that this played out last year? We didn't link these things together last year, remember? You guys learned about atomic weights in September. You learned about reaction types all the way back in January. Guys, you're going to find that some of the material that we go over this year, a lot of it will be familiar from last year, but in different orders and chunked together differently. Guys, when we talked about atomic weights, it was actually when we talked about atomic structure with protons, neutrons, and electrons. So guys, let's talk. Fundamentally, if you look at the atomic weights that are on the periodic table, guys, first of all, what's the abbreviation for atomic weight? It's A, right? Z is atomic number, A is atomic mass or atomic weight. And so guys, what does A represent? What does it tell you about an atom? The number of protons and neutrons. And guys, if you don't know this, it really should be in your notes. A, the atomic weight or the atomic mass, is the number of protons and neutrons in an atom. Now guys, what are the units for atomic weight when we're talking about the numbers of protons and neutrons? AMUs, right? So what is an AMU? What has a mass of an AMU? A proton or a neutron, right? So put that all together in your head. The atomic weight on the periodic table tells us the number of protons and neutrons. Protons weigh 1 AMU. Neutrons weigh 1 AMU. So what should these atomic masses be? Whole numbers, right? Because if you're adding up ones and ones for protons and neutrons, they should be whole numbers, but they're not. How come? Isotopes. Do we need to talk about isotopes? You're okay? Should we? Go ahead. How do you calculate average masses? Is that what you go ahead? We're about to. Yeah, well, because actually we're going to look at that because we're going to talk about the difference. You're talking about empirical formulas? Well, sort of. We'll get into it in a second. We never really calculated. No, we did. We'll do both. You'll see. We'll look at it in just a second. But guys, are you okay with the idea behind isotopes? That if you get a sample of an element, I mean, for example, if we talk about the carbon in the graphite that's not the lead of your pencil, it's actually the graphite of your pencil, what do all of these carbon atoms have in common? The 6 protons, they're all carbon, right? If it didn't have 6 protons, it's not carbon, assuming it's pure. But guys, they all have 6 protons, but they all don't have the same number of neutrons. Some of these atoms have 4, some have 5, some have 6, and as a result, even though they're all carbon, they have different masses, right? So where do these masses on the periodic table come from? They're the averages of the isotopes. And that's what you were alluding to. Guys, do you remember how we figured out the average atomic mass? Do you want, okay, so let me give you the equation. This is where you were going, right? Okay, so average atomic mass is equal to, remember sexy E? Sigma, which stands for sum, which means to add up. And it's actually the masses times the abundances, all of that divided by 100 to make it an average. So you have a problem that says carbon has 3 naturally occurring isotopes. A sample of carbon is 25% carbon 11, 25% carbon 12 and 50% carbon 14 or something like that. What's the average mass? And all you have to do is take the masses times the abundances, multiply those together, add them all up, and divide by 100. The abundances are percentages. Yeah. And I don't know if did we talk about how they come up with those numbers? Did we? So guys, let me tell you, well, here, maybe it's even in the book. Why is that?
So it's the sum.
I'm listening. Go ahead.
And so if you have the sum of something, is that just the same as that thing?
Well, so the idea, and I'm trying to find as I'm listening, I'm trying to find an example where they work through this in the book, and I don't see it immediately. So we can just talk about it. So guys, and I'm just making this up off the cuff. So if we have a sample of carbon, and let's say 30% of that has a mass of 11 AMUs, and 35% of that has a mass of 12 AMUs. What's that, 65? So, and then another 35% of that has a mass of 14 AMUs. So then to come up with the average atomic mass, we would go mass times abundance, mass times abundance, mass times abundance. Take those three products, sigma them, sum them, add them up, and then divide by 100. So it's the product of this, the product of this, the product of this,
Okay, so
added up.
just the number of those that's not of the parentheses, that's not
Well, no, so these are your masses,
Yeah.
these are your abundances.
yeah.
Do the math and add them up. Yeah. You guys okay on that? Is that coming back to you? Again, I'm not immediately seeing an example in the book, but this is what we're getting at. Okay, so we talked about these things. You understand? Well, I should ask, do you understand why they're not whole numbers? You're good? Okay. And then we talked about apparently it's on page 75. Hi. Thank you. Apparently it's on page 75. Is it really there? No, that's not even in the right chapter. There is, you know what? That must actually be from our old version of the book. Never mind. Oh, wait, but you know what? Maybe 3.4 isn't an example. Nope, it's not even the right example. Never mind. Okay. Are you okay on the idea, though? We good? Okay. All right. So, guys, with your permission, then we're going to move on and we're going to talk about the mole. Remember that magic moment when you figured out the mole is the number that allows you to convert from the AMUs that we just talked about to grams? Remember that? And I actually had a vial. I can even get it for you. I had for you. Oh, where did it go? You know what? It's gone. I actually had for you a vial of carbon. And I showed you this vial of carbon if you had me for class last year. And I said, guys, in this vial of carbon, there are 602 septillion carbon atoms. Do you remember that? And I think Miller did it too because I shared them with him. And he had this vial. It was long and skinny at the bottom. There was a little pile of carbon graphite dust down at the bottom about that big. And we said, hey, this has got 602 septillion carbon atoms in it. And then we talked about how we knew. And we remembered that Avogadro's number, 602 septillion, is the number of things in a mole. But guys, how is it we knew that there were that many atoms in the flask? Because it weighed 12 grams. And we had this moment where we understood that if one atom of carbon weighs 12 AMUs, then one mole of carbon atoms weighs 12 grams. So the masses on the periodic table are in AMUs if we're talking about individual atoms, or they are in grams if we're talking about moles of those atoms. And so we learned that the mole is the number of things that it takes for a substance to have an individual mass in AMUs equal to a mass in grams. That's that big old pile of things, 602 septillion. Do you remember that? Is that okay? And then, guys, remember, the minute we said that, the floodgates opened, and we started doing all these conversions where we went grams to moles to particles to liters. We started doing a pant load of dimensional analysis. You guys were over in lab a couple times doing those stations activities. Do you remember all of that? Okay, so guys, here's the deal. To try to go back and try to address your deficiencies relative to doing moles conversions would be a waste of time because all of you have different issues. We're going to wrap up the day today by doing some moles conversions, but guys, we're not going to spend time on it now. We'll finish the day with one, and then you'll have practice and homework so that we can make up for maybe your deficiencies as you do homework. So there you have it. All right, so guys, the next thing we're going to do is we're going to talk about empirical formulas. I told you this was going to go fast. So guys, do you remember empirical formulas? What is an empirical formula? Good for you. So guys, an empirical formula is the simplest formula for a chemical compound. If you want to write it down, you can. An empirical formula is it's the simplest chemical formula for a compound. So guys, let me show you what I'm talking about. We talked about something like this: C6H12O6, C11, H22, O11. This was actually the example I gave you in class. Some of you recognize that both of these compounds are actually sugars, and then you realize that we have a 1 to 2 to 1, a 1 to 2 to 1 carbon to hydrogen to oxygen ratio. And so both of these compounds, both of these sugars, have the same empirical formula, because an empirical formula is the simplified formula, and both of these simplify to this, and then you had the aha moment that this is carbon and this is water. So what do we call the carbon? Carbo. What do we call the water? Hydrate. And all sugars are carbohydrates because their empirical formulas are all CH2O. Do you remember that? Okay. Now, guys, we've got to go one step deeper because this is actually the definition that you now need to know for empirical formulas. The term empirical does not mean simple. The term empirical actually means based on experimentation. So if you're an attorney and you are looking for empirical evidence to prove that somebody's guilty, that means you're not looking for evidence that's based on testimony. You're looking for evidence that's based on measurement, something that you can measure experimentally. So guys, the term empirical actually means based on experimentation. In chemistry, it means simplified. Because here's the deal. Let me go back. If you take this, let me go up. Hold on. Okay, I got to go here and then go here. Okay, so if you take this sugar and if you rip it apart, imagine that if you took molecules of this sugar and you ripped it apart, what are you going to collect? You're going to collect some carbon. How much hydrogen will you collect relative to carbon? Twice as much. How much oxygen will you collect relative to carbon? Same amount, by moles, not by mass, but by moles. Now, if you take this sugar and rip it apart, how much hydrogen will you collect relative to carbon? Twice as much. How much oxygen relative to carbon? Same amount. So the idea here is it doesn't matter what sugar you rip apart, you will always collect carbon, twice as much hydrogen, and the same amount of oxygen. Here's the problem though. You don't know which sugar you're looking at. You can't figure out which sugar you're looking at by ripping it apart, because all that you know is the 1 to 2 to 1 ratio, but you don't actually know how much of 1, how much of 2, and how much of 1. You only know the relative amounts. So we call these things empirical formulas because they are in fact based on experimentation, and that's how they do that. There's a picture of it if you'd like to see. If you look on page 95. A lot of these empirical formulas they come up with through doing what's called combustion analysis. It's the picture in the upper right-hand corner on page 95. Actually, what they do is they take something like the sugar and they heat the bajinkers out of it until it falls apart, and then they capture the pieces and weigh it. Or alternately, they can burn it and then weigh the combustion products. But in either case, all that you're figuring out is relative amounts. But you wouldn't know which sugar you were actually looking at. You wouldn't know if it was C6H12O6 or C11H12O11. You'd only know relative amounts. That's why we call them empirical formulas, because they're done by experimentation and they're, by definition, the simplest ratios. You get the idea? Okay, so those are empirical formulas. So guys, with that said, we're going to do this. We're going to do some experimentation. I would encourage you to not write this down, but we're actually going to do it. Do you remember how we did this math? Do you remember we did them one beneath the other? And the first step was to convert to moles. And then once we'd converted to moles, we divided by the smallest number of moles to get whole number ratios. Is that coming back to you? We're going to do that now. So again, guys, if we have masses rather than percentages, we'll assume a 100-gram sample, and then the masses are percentages. And then we'll convert to moles, and then to find the whole number ratio, we'll divide by the smallest number of moles. Groovy? Here you go. Solve this problem in your notes. Ethylene glycol. Guys, this is actually antifreeze. This is the active ingredient in antifreeze. It's actually very sweet. That's why you don't want to have antifreeze in your garage if you have pets. If you spill it, your dogs will eat it like candy and it will kill them. It's also very poisonous. But guys, ethylene glycol, when broken apart into its elements, is composed of 38.7% carbon, 9.7% hydrogen, and the remaining 51.6% is oxygen. What's the empirical formula? Figure it out. And guys, let's just form good habits right from the start. You know you need your calculators, and I'm glad that you're grabbing for them. But guys, you got to remember here, answers without support are wrong, not just in this class, but in the AP test. I haven't worked with all of you. If you were my student last year, I'm fairly confident that all of you that I know get it. Again, I don't mean to in any way degrade Mr. Miller, but he was a little more loose with organizing your calculations. Guys, if an AP grader or I cannot follow your calculations, you don't get credit. And if you want to come back and try to argue it, you're probably going to lose. Because if I can't follow it, it doesn't make sense. Realize you can't argue with the AP graders because they don't know who you are and you will never see them. So you need to learn to organize your calculations starting now. So guys, solve this problem. You're back. Thank you. Nate, are you leaving? What? Really? I'm sorry. Apparently, they need you now. Yeah. I'm recording, so the screencast will be posted. It is. Actually, you don't know this. The homework will always be the last slide of the presentation, and it's always out of the book. You're going to see that tonight it's a little bit more than that. You're going to be summarizing something out of Chapter 4 and outlining Chapter 4, but it won't be due next time. Just look at the slides. Are you getting all 4 out? You're just going to go and let them... Good luck. Are you guys all there? Not quite? I'll give you another second. At least this. You guys all have the numbers written down, right? Okay, so with that said, I'm going to blank this out. Well, no, I'm not. I'm going to solve this down below. No, I'm not. Okay. 38.7 grams carbon. Hydrogen. So guys, if this was more conceptually challenging, I would have stepped through it with you, but frankly, and especially from seeing your responses. Hey, are you with us? Glad you're here. We're sort of here, so maybe that was inappropriate. Are you okay with what I did? Is that okay? Take the masses, convert to moles, divide by the smallest number of moles. But guys, understand that we're not done, right? You have not satisfied the question by simply doing the math, because what does the question say? What's the formula? Doing the math is not the answer. The answer is the formula. You've established the 1 to 3 to 1 ratio, but you need to then in fact write the formula, so it is CH3O. Now guys, here's an interesting question for you. Look at the masses that we started with, the percentages, and then look at how pretty the numbers worked out. Is this because I made up the problem and I just chose numbers that should work out nice and pretty? Or if we had actually done this in lab, would it work out that pretty? Which one? Did I cook the books? Or is this how nature works? Who said nature? McKay? I heard a voice. It is nature. Why? So the masses we know, the makeup is the same, but why couldn't the ratios be a little different? What did Dalton say about that many years ago? Do you remember? Do you remember? You don't remember? Guys, when atoms bond together, they always do it in whole number ratios, right? It's called the law of definite proportions, if you remember from when we did the atomic history stuff many moons ago. But the idea here, guys, is that these numbers will always line up pretty, because if they didn't, you would have fractions of an atom bond together. You can't have C1.2, H3.1, O1.7, right? They always have to work out as very simple whole number ratios, because atoms always bond together in simple whole number ratios. You can't have fractions of an atom. That was earth-shattering 200 years ago, but it's still a fundamental truth that means these numbers will always work out to pretty even ratios within the tolerances of our ability to make good measurements. So guys, do you get the idea here? Is this coming back to you? Okay, yeah.
What do we do if we do like 1.5?
Good question. You will see 0.5s and 0.3s, not typically 0.2s, but do you remember what to do? What if we had done this math? I'm going to do this and then erase it. What if we had done this math and this had come out to 1.5? You double it, exactly. If this had come out to 1.3, you would triple it. If you were dealing with really complicated, especially organic molecules, this could come out to 1.2, but then what would you do? Multiply everything by 5. So I've never seen well, to be honest with you, I've never seen a question like this on the AP test because it's just way too easy. They wouldn't waste points on it. But that said, the only examples I've ever seen, even in homework, have been 0.3s and 0.5s. So yeah, it's a good question. Okay, let me see if I can undo this. Oh, I'm scared. Oh, I did it. All right. So you guys all okay on empirical formulas? Okay, so question. What's this? Go back to the original question. What is that I just circled? What is it? We don't know. That is not necessarily ethylene glycol. That is the empirical formula for ethylene glycol, but it don't mean it's ethylene glycol. In the same way that CH2O is not a sugar, right? It's the foundational ratio for a sugar, but it's not a sugar. Sugars are C6H12O6, C5H10H5 or O5. Guys, that ratio of 1 to 3 to 1 ain't necessarily ethylene glycol. It could be, but what do we know for sure will be true of ethylene glycol? It'll be a multiple of that. It could be 131, it could be 262, it could be 393. It'll be a multiple of it, but it's not necessarily it. So now, and this is new, guys, the next thing we need to talk about is how do we know what ethylene glycol actually is? And when we ask that question, what we're actually talking about, and you want to get this in your notes, what we're talking about is what are called molecular formulas. So guys, it goes down like this. What is a molecular formula? A molecular formula is a formula that represents the compound as it actually exists. It'll always be a multiple of the empirical formula. We just need to know what the multiple is. So in order to do that, the first thing that we need to know is know the empirical formula, because the molecular formula can always be found from the empirical formula. But here's how you do it. In order to do it, you need to know the molecular weight of the compound. And then these are the steps. Step number 1, calculate what we call the empirical mass. Step number 2 is divide the molecular mass by the empirical mass, and that will give you the multiplier. Then apply this multiplier to the empirical formula to come up with the molecular formula. By the way, guys, as you're writing all of this down, some of you over the last 45 minutes have been talking to yourself quietly inside your head, going, crap. Everybody around me seems to remember all of this stuff, that Knappenberger's flying through at 100 miles an hour, and I'm pretty darn sure I'm the only person in this room that has no stinking idea what's going on. I seem to remember isotopes, but I never could have told you that the difference was the number of neutrons and therefore the mass. I barely remembered what a combustion reaction was, let alone synthesis and decomposition. And I'm pretty sure I'm screwed because everybody else knows what's going on but me. You guys understand that all that means is the people around you are much better at faking it than you are. Seriously. Guys, this first unit is going to be difficult for everybody at different times because this first unit is going to be based largely on recall from last year. Understand that in Unit 2, everybody is going to be equally clueless. But right now, all of you will be recalling different stuff from last year. You're in the process of recall. We're teaching this as if everybody recalls everything. But understand, the real recall is going to happen as you're working through your homework. And it's at that point that if you find yourself not feeling comfortable with stuff, get your questions answered. But don't look around you and have your confidence shaken because you feel like everybody knows what's going on except for you. Never compare yourself to other people in this class. I'm becoming convinced over the years that being a good AP chemistry teacher is more about psychology than it is about chemistry. You guys all know that both of my parents were psychologists, right? It explains a lot about me, yeah. We talked about our feelings a lot in my home. Okay, so guys, are you all caught up with me? You good? Okay, so now guys, we're going to tackle this question. What is the molecular formula of ethylene glycol? We just figured out its empirical formula from data. The question that we're going to answer now is, what is ethylene glycol? But in order to know that, what we need to know is the formula mass for ethylene glycol, and it's right there, 62.1 grams per mole. So what are we going to do with this? Well, guys, do this with me. Here's what, excuse me, here's what we've established. This is the empirical formula for ethylene glycol. Its final formula has got to be a multiple of this 1:3:1 ratio. So here's what we're going to do. Remember, you have steps. Step number 1 is to determine the empirical formula. So 12.0, 3.0, and 16.0. Is that 31? So the empirical mass of this is 31.0 grams per mole. Actually, guys, let me do that differently. I may as well introduce this to you now. These are going to be our units for formula mass. Get it? What does mole to the -1 mean? What does it mean if you have a negative exponent on a number? It's in the denominator. So what that means written out is this. It means grams over moles. Many times in the AP literature, you will see that they do not write labels, units, as fractions. If something belongs in the bottom of the fraction, they just make a negative sign. So for example, the speed of your car would be written like this. That's miles per hour in the same nomenclature. You get the idea? Okay. So guys, that's it. This is the mass of the empirical formula for ethylene glycol. Now what we're going to do is this. We're going to make up our own little equation that says the multiplier is equal to the empirical mass divided by the molecular mass. Now, the empirical mass, stop. That ain't right. It's the molecular mass divided by the empirical mass. So guys, the molecular mass is given to us. It's 62.1 grams per mole. The empirical mass is 31.0 grams per mole. Do the math, and that's 2. Now we know the multiplier. So what is the molecular formula for ethylene glycol? If you have a molecule of ethylene glycol in your hands, what do you have? C2H6O2. That's ethylene glycol. Where? Yeah.
What's that X?
That's my way of saying multiplier. Yeah. Yeah. You're fine.
So I remember reading a long time ago when I was studying that originally water was believed to have the formula of H2O until Dalton, I believe, was able to prove it was H2O. So probably started that way.
Okay.
The thing is, I don't know, how would they know back then that they had a bowl of water? What is going back?
It actually did, I'm, public confession, I'm a nerd. The only reason I know the answer to this is because I was actually watching a show on Channel 7 about it just a couple days ago. It was actually Lavoisier that came up with the idea. And actually what he did is after our good friend, it wasn't Volta, who built the first battery? Was it Volta? Okay, so and I'd love to know how he figured out that if he just stacked up that stack of dissimilar metal discs and separated it with cardboard soaked in salt water, you get a battery. But it was actually, once they figured out how to make those batteries, they took that battery, Lavoisier did, passed the current through water, and actually what he found wasn't relative to moles. Avogadro, it was a long time before he would have done his work, but what he did find is that the gas that collected at the negative electrode was twice as great as the gas that collected at the positive electrode. And so the positive hydrogen ions were attracted to the negative electrode, and there you got the hydrogen. And you could literally see that there was twice as much hydrogen as oxygen. Independent of moles, they saw the ratio. Yeah, and then they started huffing the gases to try to figure out whether or not they could be used as medicines until they started huffing the carbon monoxide and they almost died. And yeah. And then they found NO2, which is actually probably what he's about to go huff. That's laughing gas. And it went on from there. Are you okay with molecular formulas? Are you good? You just drinking? You guys good? All right. So guys, you are not going to have time to write down what I'm about to go over. You're not supposed to. We are going to cover the next 3 or 4 topics in one grandmother problem question thing, okay? The remainder of this chapter covers what they call quantitative information, which includes mass problems. Again, don't try to write it down. You're not going to have time. You've got a book. You can find it there. Remember the idea behind mass problems? How much stuff do you put in and how much stuff should you get out? Remember that? And then in addition to that, guys, we talked about limiting reactants. And I shared with you that very contrived idea of building bicycles, remember? And you had boxes of bike parts. And the question was, which one did you run out of first? And you may remember that if you had 100 pounds of frames and 100 pounds of wheels and 100 pounds of seats, that it actually wasn't useful to know their masses. Because when you put bike parts together, it doesn't matter what they weigh. What you really need to know is how many of them do you have. And so we said, here's 100 pounds of bike frames, but each frame weighs 20 pounds. So how many frames do you have? 0.5, and then we said the seats weigh 2 pounds, so you have 50 seats, and we figured out how many of each item we had by dividing by their weights. And then when we knew how many relative items we had, then we started putting them together as bikes. But what did we have to keep track of? The ratio they go together. 1 frame, 2 wheels, 1 seat, and because the wheels got consumed twice as fast, because you need 2 wheels on a bike, we had to take that into account as well. Do you remember? Okay, and so guys, when we talked about that, we talked about these steps. We understand the limiting reactant is the thing that you run out of first, but to figure out which one that is, just like by building bikes, the first thing we have to do is convert to moles. We do that by dividing by the molecular mass, just like dividing by the weight of the bike parts. Then we had to divide by the coefficients from the balanced equation because that accounted for the fact they don't combine 1 to 1 to 1 necessarily. And then the smallest number was the limiting reactant. Do you remember that? Okay. And then guys, we talked about the idea of theoretical yield. Theoretical yield is the maximum amount of product that you can produce given the limiting reactant that's going into the reaction. Do you remember all of that? Okay. So guys, here we go. This is where you want to start taking notes again. This is how we're going to wrap up the day. What kind of reaction is this? It's a combustion reaction. Write it down. We'll talk. I hope that in saying out loud that this is a combustion reaction, some of you went, no, it's not. We'll talk. Write it down. You guys all got it? Why should you have a problem with the idea that this is a combustion reaction? Exactly. One of our products isn't right. Remember, we said generically that a combustion reaction is a hydrocarbon plus oxygen producing carbon dioxide and water. Guys, we now need to expand our understanding of combustion. You ready? This is actually what a combustion reaction is. I lied to you last year. A combustion reaction technically involves a hydrocarbon, but it's not just limited to hydrocarbons. It can also be hydrocarbons with other things tagged onto the end of it, making them things like alcohols. We'll talk more about that later. And it always involves oxygen, but your products do not just have to be carbon dioxide and water. They can also be something like this, which is actually adipic acid. So we're going to expand our understanding of combustion a little bit to say, if you see a reaction with oxygen, and if the other reactant has any carbon or hydrogen in it whatsoever, even if there's other stuff like oxygen, it's a combustion reaction. And your products are not necessarily carbon dioxide and water. But be that what it may. Guys, here's the deal. Here's the question. I would encourage you not to write this down. It'll be on the board. But guys, it says this, just a second. It says, assume that you're starting with 25 grams of cyclohexane and 25 grams of oxygen. Now you're thinking to yourself, what on earth is cyclohexane? So let's see if we can be intelligent about this. How do we know that both of these things are reactants? Third word, assume you use, right? You're using them, you're reacting them together. So guys, let's do this process of elimination. What's oxygen? This. So what does this have to be? The other one. Or, you may remember, what does hex mean? 6. You can't be helpless. Here are the questions. What's the limiting reactant? What's the theoretical yield for adipic acid? And if you get 33.5 grams, what's your percent yield? You have 8 minutes to solve this. Then we'll do it together, and that's how we're going to end the day. You had a question, though. No, it's not necessarily. We'll talk more about it later, but no. So guys, again, what is the limiting reactant? What is the theoretical yield for acetic acid? And if you get 3.5 grams of the acid, what's your percent yield? By the way, guys, if I had you that was acetic acid, how would you know that it's acetic acid? Because it's not water. So have you all started to solve the first question? So let me give you this. There's the steps for doing limiting reactants. Is that helpful to leave out? What? Oh, we'll come back. I'll come back to it. It was actually theoretical yield, I think. Yeah, what's the theoretical yield for adipic acid? Here, let's do this. Okay, guys, the steps are on the board. There you go. Probably shouldn't have given those to you, but kind of a softie. And again, guys, remember organization. Label your numbers. Watch significant digits. If your paper looks like chicken scratch, you're not okay. If you're not sure when you're all done, hand it to the person next to you if you know they'll be honest with you and ask them, can you follow this? If the answer is no, you're in trouble. Spencer, do you want this? What's that? My daughter will never know that I gave this back to you, so it'll be fine. Because what I'm going to do as you continue to work on this is I'm going to start stepping through the solutions about 5 minutes behind you, because you can't do question 2 without question 1. But some of you could do question 2 but can't do question 1. And this is very common in the AP test where question 2 relies on question 1. Just got to get used to it. So I'm going to work on the first question. So guys, if you'd like to see the work that I did with the first part of this problem, I believe that the cyclohexane is a limiting reactant. Can you confirm that? Okay. Understand that technically you should then write out a sentence that says cyclohexane is the limiting reactant. I'm not going to do that to save space. Go ahead. Are you guys all okay with the first portion of this? Notice that we divided by the coefficients and not the smallest number. That's empirical formulas, and they look sort of the same. Now guys, let's give you a boost if you're stuck here. How do you figure out the theoretical yield? What do you start with? It's a mass-to-mass problem, but what do you start with? The 25 grams of the cyclohexane or the 25 grams of oxygen? Why the cyclohexane? It's the limiting reactant, and that determines how much product you can make. So the next part of this problem then is a mass-mass problem that starts with 25 grams of C6H12 and works out to grams of adipic acid. Did anybody figure out the mass of adipic acid? Can anyone confirm that? 146?
Yeah.
Thank you. Not that I don't trust you, Caleb, but what did they say? Trust but verify? So guys, as a result of that second calculation, my numbers say you should get 43.5 grams of adipic acid. Can you support that? Okay. Then guys, the final calculation that we didn't talk about specifically in class is the percent yield. You may remember that percent yield is actual divided by theoretical, where the actual yield given in the problem is 33.5 grams. The theoretical yield is 43.5 grams. That's multiplied by 100. Is that like 75%? 77 point some significant digit percent. Is it a zero? There we go. So guys, this is something that you're going to become more and more comfortable with as time goes on. Problems that build on themselves. Every single problem in free response that you see on the AP test will be a multi-stage problem, where if you can't do A, you can't do B. And it builds on itself. Each one of the steps of a problem like this is worth a point. Typically then they'll range between 7 and 9 points because they have 7 to 9 parts. It wouldn't be a problem like this. This would never make the cut for an AP test. But it's sort of this idea where you have multi-stage problems where each step calls upon a different concept or skill. So, questions about any of this? You okay? That was a lot of stuff, and I understand that. Guys, when we get into chapter 4, we're actually going to spend 4 days in chapter 4. We're going to slow down. There's a lot to learn. So really, you're okay here? Okay, this is, I think, going to be horribly ghosted. Yeah, so let me do this. Get out of here. And guys, I want to talk with you briefly about your homework before we call it a day. So this is your homework. All of these are out of the end of chapter 3. The answers are posted online. When I see you on Tuesday, as you walk into class, guys, grab your books, open them up to the end of chapter 3, grab your homework. When the bell rings, I take roll, and then we say, what questions do you have? And we spend sufficient time to get your questions answered. Now, guys, in addition to that, and McKay, this is what I was speaking with you about. Well, not quite yet. You are going to outline chapter 4. And I know that I told you last time that we are not going to do outlines after chapter 4. I do want you to have the experience of outlining a chapter. Simply because right now, for most of you, that's all you know. You've only interacted with a science tech by outlining. And I want to bring you back to that so that when we do more of this throughout the first semester, you have that experience of doing that to see how these other strategies compare. Guys, this is not due on Tuesday. It's due on Thursday. And then, McKay, this is what I was talking to you about. On page 121, this is the solubility table. What I want you to do is summarize it. Remember, guys, this is all about return on investment. Your goal is to take that table on page 121 and distill it down to 4 or 5 or maybe 6 fundamental principles that will allow you to know cold the solubilities of most things. If you're not sure what that might look like, talk to McKay, because he and I talked through it earlier this morning. This is due Tuesday. So these 2 things are due Tuesday. That's due Thursday. Okay? Bless you. So guys, I'm going to stop recording.